Alright, so I want to make a little video concerning the precise definition of a limit for a sequence. So let's get to it. So here's the definition. We say the limit as n goes to infinity of a sub n is equal to L, provided that for each epsilon greater than 0 there exists a natural number n, alright, such that n greater than or equal to n implies that the absolute value of a sub n minus L is less than epsilon. So this careful definition captures this idea that, if you have a sequence which converges to L, if you go far enough out in the sequence, you can get closer and closer and closer to L. Or to be more precise, if you pick a specific tolerance, if you will, epsilon band about the limiting value L, there exists a point sufficiently far out in the sequence in which everything else in the sequence is within that tolerance of the limit. So this is the precise definition for a finite limit. Now, there's also a definition for a limit that goes to infinity. All right. In contrast definition, we say the limit as n goes to infinity of a sub n equals to infinity if for every m greater than 0 there exists an n in the natural numbers such that n greater than or equal to big N. Put some feet on my big N so you can tell the difference. Actually, I guess that's more than feet. I don't know what that is. But anyway, I'm decorating them. Such that if n is greater than, little n is greater than or equal to big N, then an is greater than m. So this careful definition here basically is saying, if you go far enough, if you want to make it bigger than m, well, if you go far enough out in the sequence, it's bigger than m. Such a sequence, of course, is said to be unbounded. A similar definition can be given for negative infinity. Now, we saw both of these kinds of sequences in the example video, but I have not given these kinds of careful analysis, precise definitions to say anything about the limits. We just kind of used our knowledge of pre-calculus and or other things we saw in Calculus 1 to come to an understanding of what those limits were, right? But these are the precise definitions in the background. So let me just do at least a token example and maybe one property. So here's an example. Alright, so allegedly, if we take the limit as n goes to infinity of 1 over n, that's equal to 0, right? Let's see here, how would we prove that? So let me put some scratch work. I'll put scratch work over here. So scratch work, what do we want? We want 1 over n minus 0 to be less than epsilon for n greater than or equal to some n. We've got to figure out what that n is. Of course, this just gives me 1 over n is, n is positive, right? So that's 1 over n is less than epsilon. Okay, great. So, well, that suggests that 1 over epsilon is greater than n. Aha. So here's the proof. Let epsilon be greater than 0. Suppose n is a natural number which is larger than 1 over epsilon and smaller than 1 over epsilon plus 1, just to make it precise. Alright, so like if epsilon is a third, then then my n would be 1, right? In fact, I think n is pretty much going to be 1 if epsilon's small at all. Alright, so usually this would make n equals to 1. I believe this is the so-called ceiling function, right? So I'm letting n equal to the next integer bigger than 1 over epsilon, right? Sometimes this notation is used without the... Sorry, I didn't mean to put a... There, like, this is the ceiling function. Alright. Then, if n is greater than or equal to n, we have n is greater than or equal to 1 over epsilon. Thus, 1 over n is less than or equal to, well, let's see, I don't want the equality, so I should, let's see here, how can I fix that? Let's add 1 to this just to be safe, alright? If I add 1 to this, then I definitely have I have a strict inequality here. So 1 over n is less than epsilon, and so you see the absolute value of 1 over n minus 0 is less than epsilon, right? Thus, the limit as n goes to infinity of 1 over n is equal to 0. Alright, there you go. So obviously this could be more exciting if the function is more complicated, but this is something like this is how we give careful proofs that limits went to whatever they went to for a given sequence. Let me show you a proof I always would show in the residential section. I mean, I say always, but, well, let's say this is a proof I should show the residential section. Whether I actually did in a given semester is a complicated question of many factors, but here's the theorem. If a sub n goes to a and b sub n goes to b as n goes to infinity, then the sum, right, a sub n plus b sub n goes to a plus b as n goes to infinity. Of course, we could write this with limit notation instead. Limit as n goes to infinity of a sub n equals to a, and the limit as n goes to infinity of b sub n equals to b. If these two conditions are met, then the limit, and to be fussy, I really should say for big A and big B real numbers, right? And all of the sequences I've been talking about in this this video have been real sequences, okay? Alright, so that's a theorem. Basically says that the sum of convergent sequences is convergent and it converges to the sum. And here's the proof. Alright, so let's get to it. The proof looks like this. Proof. Let epsilon be greater than 0. Choose n sub a in the natural numbers such that n greater than or equal to n sub a implies that the absolute value of a sub n minus a is less than epsilon over 2. Also, choose n sub b in the natural numbers such that n greater than or equal to n sub b implies that the absolute value of b sub n minus b is less than epsilon over 2. we can choose such n sub a and n sub b, since the limits, a sub n goes to a and b sub n goes to b are given. All right, let n equal to the max of NA and B. Then observe the absolute value of a sub n plus b sub n minus parentheses a plus b is equal to the absolute value of a sub n minus a, parentheses, plus b sub n minus b. Now at this point, I have to use something called the triangle inequality for inequalities. So triangle inequality says that that's less than or equal to the absolute value of this plus the absolute value of that. But you see then we're in business because notice that by construction, oops, I forgot something important, which was to write, let me write it in here right here before I forget. This is actually kind of important. For n greater than or equal to n, right, we have two things. We have n greater than or equal to na, but we also have n greater than or equal to nb. And so that means that I am able to make this step. This is less than epsilon over 2 plus epsilon over 2, which of course is equal to epsilon. Thus, by the definition of limit, the limit as n goes to infinity of a sub n plus b sub n is equal to a plus b, which, by the way, is the limit as n goes to infinity of a sub n plus the limit as n goes to infinity of b sub n. So there you go. That's a a nice proof of something, a property of sequences. Now, I will tell you this, that a careful proof can and really should be given for the product of sequences, but that one I wouldn't be able to do off the top of my head so easily. Like, the product of sequences is a little bit harder to prove. And in any event, I will try to include those kinds of proofs in the residential lectures, hopefully next semester. If you look back in previous semesters, I'm talking relative to 2018, you'll find them in there somewhere. Or contact your instructor, of course, if you're curious. But anyway, I think I'm going to leave it at that. Just wanted to give you a sense of how we would prove these things carefully. If you're a math major, you will eventually get back to these things in your real analysis course, but there it will go much faster. So anyway, thanks.